Okay. This presentation is for Professor Zhan on behalf of the Tsinghua University team. On Tuesday, we talk about the temperature dependence of excess heat power discovered by at storms. The dependence is very similar to temperature dependence of diffusion coefficient, just like this, E to the minus activation energy over temperature. This behavior has been supported by Freshman Pang's heat after death experiment. Both of them are electrolysis experiment. Now, I'm going to talk about the gas loading experiment in 3 years at Tsinghua University to have additional support to storm's straight line. Indeed, we notice this straight line in the cold fusion forum, this plot cited by Bill Collis. When I saw this dependence, I immediately go to my original data because we studied excess heat dependence on temperature early in 90s at these 3 temperatures. When we draw these 3 temperatures, the slope is not the same as that at the storms. So we try to use Freshman Pang's heat after death experiment. Because he gave 11 points at different temperature. At the beginning, we just used the first 10 points. It looks like a straight line, but the slope is a kind of uncertain. Fortunately, he has a lower point temperature here, 31 degrees. Then make this straight line behavior very confident, but the slope is different. So we try to go to lower temperature. Fortunately, we did the cooling experiment in gas loading phase. One bottle filling with deuterium gas, one bottle filling with hydrogen gas. Both of them totally similar with palladium inside. When they are cooling down without heating, if deuterium bottle has some excess heat in it, its cooling behavior must be different from this one, should be cooling slower. From this data, I figure out this point. Then we go to lower point, because at that time we try to calibrate the thermistor. How do we know the thermistor is correct? We do not have NIST. But we can try this way. One is the room temperature thermistor. One is the palladium thermistor. If they are equal, this temperature should not change. If this room temperature is a little bit higher, palladium temperature will go up until they are equal. If this is lower, palladium temperature should go down until they are equal. So if we look at the temperature curve, they are supposed to intersect at the peak and at the lower point. Then we say these thermistors are reliable. If this temperature goes up, this room temperature is still lower than palladium temperature, we may say there might be some extra heat inside this palladium wire. Fortunately, the gas loading experiment is very sensible because its heat conductivity is low. 1 degree difference almost means 12 milliwatts excess heat. So down to this point, we figure out about 3 milliwatts, but it's still on the straight line. Now, let's go back to first these 3 points for the excess heat at fixed temperature. First, we should talk about why did we do this experiment. Indeed, the heat after death experiment has the last period. The electrolyte boil to dry. There is no electrolyte beyond. So why do we need electrolysis? Maybe we can use gas loading to load this palladium wire. Then we can use electricity to heat to 100 degrees. Then we can pump out the deuterium gas to create a flux. It's very similar to the last period of freshman Pound's heat after death experiment. If we succeed, it's a good reproduce of freshman Pound's heat after death experiment. So we switch to gas loading experiment and use a long, thin wire, use electricity to heat it to 100 degrees. Then we pump it. That's a device we used for 3 years. Outside is vacuum dewap, stainless steel. The green one is a quartz shelf. On this shelf, the blue line is a long, thin palladium wire. The red line is a tungsten. Why do we use tungsten? Because early in 1972, an expert for hydrogen loading said they did loading using tungsten wire 2,000 Kelvin, and their loading is higher than 0.9. It's reproducible, and it's very good for different source of palladium wire. So that's very important for our experiment. So we put the palladium wire in, and we can fill in deuterium gas and pump it out. The problem is the heating. How do we keep it at a constant temperature? We know if excess heat comes out, the temperature will change. If we can control the power, then the power reduction will be a measurement of the excess power. How do we control the power? At that time in my lab, we have only power supply with constant voltage, a power supply with constant current. We do not have an intelligent power supply to use a temperature sensor, control the constant temperature. Fortunately, Professor Zhan at that time was very smart undergraduate. I asked him, if you can modify existing power supply into an intelligent power supply, he said, let me try. Fortunately, he succeeded. We start from the 95 degree. You see, from here to there, 5 degrees. So his intelligent power supply works pretty well. This is about 2 days, control very well. And this is power about, this is 2.5, this is 2.0. So that's about 2.25 watts. At this time, we start pumping. you can see at the beginning there is a jump. We know when the deuterium gas leaving the palladium wire, it's endothermic. So the power comes up, then reduced. That's reduced by more than 1 day. Then we stopped here, and the necessary power goes back to the original value. So we start pumping again. This phenomena appear again. Now we try to go to 100 degrees as freshman pounds. We change the specified temperature just by increase the power here. Here we still have pumping. Then we start pumping here, the power jump again and go to this value. So this difference is a measurement of excess heat. It's about half a watt. It's a reproducible, it's controllable, it's sustainable. It's a kind of heat after death experiment. Why we didn't continue? At that time, we worry about the pumping will change the pressure, will change heat conductivity. So the necessary power dropped. We have to exclude the effect of heat conductivity. Later, we did this experiment. We use a valve to control the pumping rate. We can reduce the pumping rate by controlling the valve without stopping the pumping. That's necessary power for 50 degrees. Then we start pumping with half open valve. So it just comes down this way. We turn a little bit back. The pressure goes up. We are still pumping. You see, the necessary power didn't go back. So heat conductivity goes back. The power didn't go back. Then we turn the valve down to the end. So we got this. The pressure go down. At this point, we stop the pumping again. The necessary power goes up back to original value, and the pressure goes back slowly. Please compare these 2 points. This point and this point, gas pressure is almost the same, but necessary power is different because here has no pumping. So this is a good experiment to support our result. And this we gave the third point for 50 degrees. Now we talk about a twin system. One is hydrogen bottle, one is deuterium bottle. The weight for palladium wire is almost the same. The tungsten wire is a little bit different. We pump them both down to the 10 to the minus 3 Pascal. When we fill in deuterium or hydrogen, both to 600 millimercury. Let's see what's the cooling curve. The up curve is for deuterium bottle. Black one is for hydrogen bottle. At the first period, they are very close, and this one is faster, this one is slower. So there must be some heat inside the deuterium wire. How much is it? We can extend because this curve can be fit by a famous equation. It will give you the final temperature. The difference is about 1.1 degree. So it's about 13.2 milliwatts. That's our first point. Now, we look at the fifth point. That's in the winter. We put this deuterium bottle inside a thermostat. So the thermostat will act to keep this water bath constant temperature. So you will see the black peak, 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 that's thermostat action. And this red line is the thermistor on the palladium wire. Look at this intersection at the peak, at the down, peak, minimum, minimum. So we say it's not NIST, but it's accurate enough. However, 2 days ago, the picture is different. The black one is the thermostat action. The red one, you see above the black one, it's still going up, going up, going up. So there must be something inside the deuterium bottle with this calibrated thermistor. So we just estimate it this way. The difference between red line and the black line is this blue line. So up, down, up, down. So positive, negative, down fast because it's start action. So how about this one? The difference is about 0.6. This is 0.3. This thermistor is calibrated. It's enough to measure the 0.1 degree. So this 0.3 is reliable. It gives us the fifth point. So that's our straight line from gas loading. It supports at storm's behavior and freshman ponds heat after death. This is electrolysis. This is gas loading. Before we say freshman ponds heat effect is a real effect, we did one more experiment. We tried to create a situation. There is a strong pumping without strong flux. And compare with the situation, there is pumping with a strong flux. What's the difference? Remember, if this is the tube, we fill both sides palladium gas. We pump inside and create a flux from outside to inside. But if we pump both sides, the pumping is there, but the flux is reduced a lot. So let's see what happens. Okay, that's enough. That's 7 long, thin tube, 40 centimeter long, 7 tubes. Inside the deuterium bottle, inside a glass dewar. This is parameter show its accuracy to measure 20 milliwatts. Indeed, we saw in the order of watts. We pump inside only, then outside gas pressure change only a little, no big change in heat conductivity. When we pull both sides, the heat conductivity is reducing. So we expect the necessary power is reducing. However, we see this behavior. This is the temperature fixed at 150 degrees centigrade. This one is necessary power. This is the pressure outside deuterium tube. At the beginning, outside is deuterium gas. Both sides is pumping. There is flux. This is power supply. At this point, we pump outside. Strong pumping, less flux. The necessary power increase instead of decreasing. So this is a strong support to our judgment. The flux is more important than pumping. So I would like to go back to this conclusion. freshman pond's heat effect is a real effect. It's reproducible, it's controllable, it's sustainable more than one day. Many thanks to Cold Fusion Forum. Is Nikita Alexander here? Because this forum, we go back to our original data. Thank you.
Very interesting talk.
I would like to thank you for focusing on this variable because it's incredibly important. It has essentially three features to it that are important. The first one, the slope and the activation energy, gives insight as to the mechanism of the nuclear reaction. The second is that this is characteristic of the Pons-Fleischmann effect. And by measuring it, you have another way of proving, as you demonstrated, that the effect has actually occurred and you're not looking at error. And the third is that clearly, if you're going to make this a technological, have any technological benefit, you're going to have to work at the higher temperatures to get the larger amount of heat. And you made that point also. So I thank you very much.
Thank you, thank you. Indeed, we worry about these low temperature data at the beginning because I was a student to do experiment because I am a theoretician. I rely on my student. So for this kind of point, I just say it's qualitative, say there is excess heat. I cannot say it's quantitative. Because of Storm's curve, straight line, I believe this result more.
Okay, Francesco.
Okay, it seems that your data comparison, okay, it seems that the data, the experiment comparing deuterium and hydrogen system and pumping or flux, the key parameter, is similar. Remember the experiment made at NASA from Gustav Freilich in '89 and after replicated with more sophisticated materials in 2008-9. So they are in very close agreement. So I suggest you contact Freilich.
Thank you very much. I have to thank Professor Biberian. He gave me NASA work after ICCF-9. I obtained this result, and I was so happy. And I met them in Missouri. And later, they cite our work when they report in NASA. Now we support each other.
Yeah, very
Thank
good
you.
point. Okay, thank you.
Okay. Peter.
I have a really simple-minded thought. If you can get a fraction of a watt out just by fluxing deuterium gas through your membrane at 100 C, why not crank it up to 200 C or 300 C or 400 C if you've got a line going up exponentially? You'd have a, I don't know, a useful device that you could start marketing here.
That's your duty. I have no student now.
Okay. Is there any other? Please.
The flux being important, it seems like it would be useful to do some experiments on different types of palladium, crystal sizes, for example. And I think you probably could even model the microscopic aspects of the crystals and then get a correlation between metallurgy of palladium and flux rates, which seem to be important.
Thank you, thank you. Indeed, we have to do more work. You see, after 1 day pumping, where is the deuterium gas from? We worry about this, and we try to solve this problem just as you said. We calculate the chemical potential along this palladium Y and see if there is any circulation. Due to the pumping, we change the working point, and the working point is critically important for this circulation.
Okay, thank you. Just chat time. Thank you again, Professor Lee.